Hey, we've got Adam and Zach already. Good deal. People are showing up for the 1 o'clock class here. Excellent. Why does it say a big blue Z up here at the top? What on earth? Oh, that's Zach. That big blue Z is Zach. Okay, that's and Adam. That good for you, Adam. Glad you're here. I put some equations up on the board. You guys might want to copy those down. I need to put them on Blackboard for you. I was going to, but I don't know if I did or not. But we'll go over them here in a minute after we get a few more customers showing up. I've got to go get my water bottle or I'll get dried up here. Let's see. I'll be back. Go get my water bottle. Oh, there it is. I found it. We're actually going to be in chapter 14 today, I believe. But these are nice equations from chapter 12. Hey, we've got Ben also. We have another customer. Any of you guys? Hey, look at there. There's Brandon. Good. Excellent. Any of you guys have a comment or question? Well, I'll ask you some questions while we're waiting on the others. This equation right here. See that equation? It's got a name. Let's pick on my friend Ben. Ben, unmute and tell me the name of that equation. Ben?
That's the magnetic field of a wire, isn't it?
Well, that's kind of, Ben, but it's for a very little teeny infinitesimal piece of that wire. And it's named after two French guys. It's a very famous equation. I'll give you a hint. It starts with B. The Butler-Smithsonian equation. No, that's not right. The Bouvier, that sounds French. The Bouvier Seminar equation. No, that's not right. So, the Bouvier's savoir-faire equation. No, dang it. I give up. What do you think it is, Ben? Guys, if you just tuned in, we're asking Ben what the name of this equation is here. This equation right here. It's got a fancy name. It's named after two French guys.
The name is currently escaping me right now.
That's okay. That's fine. It's the Biot-Savart law. The Biot-Savart law. That's the name of it. Well, we'll pick on somebody else. Now this equation right here, let's pick on my friend Chris. Chris.
What? I just got here. I don't know what we're doing.
You lucky guy. We're going to pass over you. Mohammed. Hi there, Mohammed. Hey, Mohammed.
Yes, sir.
This equation here, it really doesn't have a name, I don't think, but it's very important.
Yeah, it's used to find the magnetic field for the long wire. It's derived from the Biot-Savart law.
Yes, good going. Here, let me write that right here. Mohammed's absolutely right. It's a magnetic field of a long wire. Now we're going to click on somebody else here. Zach, the big blue Z on my thing here. Unmute, Zach. Unmute. I want to know what the, well, this doesn't really have a name, but what's it for?
Isn't that to find the magnetic field of lead just like a regular wire?
Yes, yes, exactly. This is a magnetic field for a short piece of wire. Good going, Zach. How come you, Zach, how come you come up a big blue Z on my thing here?
It's because I'm using an application and I've signed in on my Google account, so it's using my Google icon.
Pretty cool. I like that Google icon. That's really slick. That's for a short wire. Now this one here, we'll pick Kristen. Hello, Kristen. Come in, Kristen.
Yes, sir.
Hey, Kristen, did you try to log in this morning at 9:30?
Yes, I did. And I never could get it to work for me.
Okay. I ran into problems. And so you're not the only one. Everybody ran into problems. However, I went ahead and recorded the lesson. And, you know, fascinating, excellent lecture as always.
Mm-hmm.
But my daughter won't be able to put it on YouTube till she gets home from work tonight.
Okay. Was there homework assigned during the lecture?
Oh, gee. Oh, gee. Yeah, there was. However, it's not to turn in. It's just for the pure pleasure of doing it, okay?
Okay, that's fine. What was it, sir?
I don't know.
Are you asking about the last homework problem that was assigned?
Well, for this morning.
Yeah,
For
hey,
dynamics.
just a minute, Kristen. I have it right here. Just a second.
Thank you, sir.
Don't his lectures start at 1, or does he start before that?
They have another class with them.
Yeah,
Oh, okay.
This class, it starts with 1, but I have 4 classes with them, so I do these a lot.
Okay, that makes sense.
This is for Kristen, and
Okay.
the rest of you don't pay any attention. It's a yo-yo, Kristen, and it's
Okay.
problem 1821. It's not to turn in, but see if you can do it. It's on page 493.
Okay. Dynamics. All right, perfect. Because I'll just put a note not to turn it in, but I still want to do it.
Yeah. See if you can do it.
Okay, perfect.
Now back to Kristen. Kristen,
Yes, sir.
You see this equation right here.
Yes, sir.
What's that one for?
Well, it's for finding a magnetic field, and I believe it's for, is it for between wires?
Nope.
Oh, okay. I don't know.
Well,
It's not for a short one, I know, because the short one uses the angle, so I don't know.
Yeah, this one here is the short one here.
Yeah.
Now this one here, Kristen, this is if you have a
Oh,
circular.
is it for like the solenoid? No.
No, it's not a solenoid.
Damn it.
Kristen,
Okay.
If you have a circular, this equation here is for a circular loop, a current loop, okay?
Okay.
Circular current loop, and that gives you the magnetic field coming out straight out at you at the center of your circular current loop.
Okay. Got it.
Now, as long as we're talking to Kristen here, Kristen, this one here is also for a circular current loop. But this one here is if you come out here at distance x and you want the magnetic field there. And here's your current. your currents going around and around. This equation, they're both for circular current loops, but that's along the axis of a circuit. Now we're going to ask somebody else. Logan, unmute. Hey, there he is. I see him.
Yeah. Hello.
Look, you see this equation right here?
Yes. B equals mu times n times I.
What's it for?
Let me consult. Can you tell me what what the units for
Yeah.
n is?
N is the number of turns per meter.
Oh, okay. So that would be the one with the coils, right? It would
Yeah.
be the magnetic field inside of the coil.
Yeah, what's the name of that?
Oh, I have it in my notes.
It's got a fancy name. You have one in your car.
Solenoid?
Yeah, that's it.
Okay.
That there is for solenoid. Good going. Logan, proud of you. Now this last one, nobody will know that last one. I don't know if we even talked about it. But let's go to my friend Brandon. Brandon, unmute. Unmute, Brandon. Earth calling Brandon. Unmute, Brandon.
Yes, sir.
Brandon, do you happen to know what this one is for?
I do not, no, sir.
Nobody does. It's okay. That's a toroid. I don't know if we even talked about toroids. That R is the radius of your toroid. Don't worry about it right now, but there's a bunch of equations, some of which we have studied, and some are terribly important. And now I want to talk about something they all have in common. All of these equations have something in common. Well, one thing they have in common is they all have that mu sub 0 thing, don't they?
Mhm.
Yeah, they all got that mu sub 0 thing in it. What else do they have in common?
Aren't they all derived using Ampere's law?
Actually, they were. Some of them were. You can derive some of them with Ampere's law, but you could also derive them with that Biot-Savart law. See, this one's the Biot-Savart law.
Mm.
All of them is directly proportional to the current. The magnetic field strength is directly proportional to the current.
They all have a current. If
Yes.
you look at every one of those equations, everyone has a current. Now, I was telling you guys this, I think last time, that the magnetic field is a function of the current. Kind of like you guys have studied functions, you know, f of x equals 3x squared. There you go. You've all in algebra seen functions of x. Well, the magnetic field is a function of the current. Look, there's the current. Look, there's the current. For any given one of these things, all of this stuff is pretty much a constant. The current, it's the current times some kind of constant. Okay, good, we know that. Now here's something else. Magnetic flux, we know what the definition of it is. The definition of magnetic flux, yeah, I got it right this time. I keep hearing somebody playing the high notes on a harmonica. Now, who's doing that? And then there's somebody squirting water in a sink and playing high notes on a harmonica. Very entertaining. But do you notice the magnetic flux? They quit. They turned off the water. How about this? Quiet. Magnetic flux is a function of the magnetic field. Well, yeah, of course it is. Now think about this. magnetic flux is a function of the magnetic field, and the magnetic field is a function of the current. So if you wanted to do, what is it, Faraday's law, I think I showed you this, but I'll show you again. What I'm trying to tell you is the magnetic flux is a function of your magnetic field. And magnetic field is a function of your current. So magnetic flux is a function of your current. That kind of makes sense to me. Now, Faraday's law says that your voltage is equal to negative, well, if you have more than one turn, you have to go in terms times the derivative with respect to time of your magnetic flux. But since magnetic flux is a function of current, they've come up with this equation here. And there's just going to be some kind of constant here, and they decided to call that constant L, and they gave it a name, and they called it inductance. That's the name of this. And I think last time I told you the units were ohm seconds. The units for inductance are ohm seconds. And now we're going to take these two equations and set them equal. You either need to write all these down, or I need to put them on Blackboard for you. Let me erase this. I need the room here.
Well, this whole lecture is being recorded, right?
Yes, this whole lecture is going to be recorded, right? Surely. Yeah, it's a wonderful lecture here. Okay, so what I'm going to do here is I'm going to set these equal to each other. That's the voltage according to Faraday's law. You know what? This is really just another version of Faraday's law. It's another version of Faraday's law, and it's equal to this here. Now we're going to do a little algebra on this. Hey, we could get rid of those DTs and the minus signs. We don't need those stinking minus signs. See if you can get to here with me. We just lopped off those DTs, did a little algebra there, got rid of the minus signs. Now, if you integrated both sides, L is a constant, N's a constant, just the number of terms, and you integrated from 0 to some final value, what you'd have is this here. And here you'd integrate from some 0 to some value, final value of current. By Jove, that's what you'd have. And so now we can write an equation for inductance. Ta-da! We just did. Did I do it right? Yeah, I did it right. And this is in your book. Let me show it to you. Let's see if I can find it here. This is chapter 14, I think. Yeah, let me dig around here a little bit. Okay, it's on page 640. They wrote this equation here on page 640 in your book. You can get the units of L from that even. See, N is number of turns per meter. So that would be 1 over meters. flux is Tesla meter squared, and current is amps. So another way of expressing inductance is Tesla meter squared over meter times an amp. Probably need a line there. Hey, we could get rid of that meter. You know what? And you could get, it's a Tesla, you know what? It's a Tesla meter per amp. That's one way of expressing it. There's different ways of expressing inductance. The symbol for inductance, by the way, is a deal like this. See, we've studied resistors. That's a deal like that. Capacitors, they look like that. These are inductors. And the units are Tesla meters per amp. Now, a Tesla is a Newton per amp meter. So you could write this as a Newton per amp meter times a meter over an amp, which would give you a Newton per amp. An amp you could write as a coulomb per second and leave the other amp like it is. Wait a minute, I did something right. No, I forgot this other meter, didn't I? Okay, now just a minute. Newton per amp meter, meters. Oh, guys, I think I just screwed up. Let me see. I was doing so good, and I understood what I was doing up until this moment, and now my whole universe is caving in on me. I think we did this right. This is correct. We found it in the book. And here's my problem. No, that doesn't have units. That's dimensionless, isn't it? It's just the number of, yeah, that's where I made my mistake. The units of N are not 1 over meters, guys. That's a screw up. See, that's why I need you guys alive with me. The units of N is nothings. So what you have here is a Tesla meter, Tesla meter per amp. Okay. All right, now I fixed my problem there. Now, a Tesla is a Newton meter per amp.
Tesla meter squared.
Yeah, it should be
Absolutely. You're absolutely right. I heard that voice. I don't know who it was, but I heard it.
It was me.
Well, thank you.
Wait, I thought that we canceled one of the meters out.
We did, but we did that incorrectly.
I had a meter that didn't belong there. The units for N is nothings. And the units for flux is Tesla meters squared, and amps is amps. And we're going to be fine now. The unit for Tesla is Newton meters per amp. And we don't have a meter there. We have a meter squared here. But there's another amp there. And so what we have here is a Newton meter squared over a coulomb per second amp. Okay. Well, a Newton meter is a joule, and a joule per coulomb is a volt. So what you get here is a volt.
Volt second per amp.
A volt. What about that squared though? It's a volt meter second per amp. You're not supposed to have that meter here. I've got an extra meter. Driving me nuts here. Okay, now let me stare at this a minute. let me do it step by step. Inductance is equal to N. Here, we'll write it out. N is dimensionless. It's just a number of turns. Not per meter, just turns. And flux is Tesla meters squared. It's foolproof plan here. You guys are with me. Some of you are awake, and I appreciate it. And current is amps. All right. Now forget that nothing. We don't need that. Now we're going to write, see, a Tesla, I believe, is a Newton per amp meter, isn't it? Yeah. Is that what a Tesla is? Let me make sure I get this right. F equals I L cross B. So a Tesla is a Newton per.
Yes.
Yeah, that's right. A Tesla is a Newton per amp meter. I get that from this equation here. That's where it comes from. See it? This equation here. Okay. So now we're going to put this inductance is equal in units. It's equal to a Newton per amp meter. And then you have a meter squared.
Yep.
Over amps.
Also, yep.
Over amps. Now we can get rid of that meter there. And we have and we can write that as a coulomb per second. And we have a joule per coulomb. What we come out with is a volt second per amp.
Yep.
And a volt per amp is a ohm. So you get ohm seconds. Ta-da! So you can write inductance as a volt second per amp, or as an ohm seconds, or as a, what was the other one we had? I got lost.
Henry.
Yeah, Henry, exactly. Yeah. Or a Tesla meter squared per amp. Here, let me write all of those for you. I'm going to write all of those for you. Inductance can be written as a Henry. And a Henry is equal to an ohm times a second. And that's equal to a volt per amp, a volt second per amp. And finally, it's also equal to a Tesla meter squared per amp. Sorry to confuse you, but the one I like the best is this ohm times second. Of course, Henry is what it is. So we've got ourselves the units for inductance. And we have an equation here, right here. Yeah, right here. Thank you for suffering through all that with me. And now what we're going to do is get the inductance of a solenoid. I need a little room to do this. How about up here? Yeah. What we're going to do right now, for those of us that can just barely stay awake, is we're going to get the inductance of a solenoid.
Your mic is starting to crack again.
Oh, here, let me, thanks for telling me. Let me unplug and plug it back, and maybe we'll get lucky, I hope. Okay.
Yep.
It's okay for right at the moment?
Yeah, sounds good.
All right. Now here's what we're going to do. We're going to find the inductance of a solenoid. Okay, now N is just the number of turns. That's not a problem. Now the flux. The flux of a solenoid is the magnetic field times the area. See, magnetic flux is the integral of B dot dA. But we don't need no stinking integral because it's just constant inside. So you can pull the B out, and when you integrate the little dA, you just get the area of the solenoids are usually round. It's just that circular area there. Don't forget the NBA. Isn't that the National Basketball Association, NBA? I think it is.
Yep.
We know what B is. I feel like I'm going to sneeze. I feel a sneeze coming on. Maybe not. We'll see. I've got a formula for a solenoid. It goes like this. Ta-da, and that's it. And there's the area, and there's the eye. Now here's the beautiful thing. Those eyes are going to cancel out. You see that? Those eyes cancel out. Just lop them off. We don't need those stinking eyes. And we could just write it like what we have left. But what they did in the book is they said N, little n is big N over L. So they went N mu sub O big N over L. That's not an I. We got rid of the I's. Times A. I didn't forget anything, did I? No, I think that's it. Yay, that's it. So bottom line, the inductance of a solenoid is mu sub O N squared A over however long the solenoid is. Now I'm going to look in the book and see if we got that right. Okay, I'm looking here. Boy, Jove. This is on page 643. In my book, on page 643, they say mu sub O N squared A over L. Yay, we got it.
So the inductance that we got before, that was L equals N times the flux of B over I. Is that for a solenoid as well, or is that for a different thing?
This here is, it's for a solenoid, for sure.
Mm-hmm.
But your question is, will it work on other things? Right?
Yeah, so are all the equations that we've done right now with inductance, are all of these used for solenoids, or can they be used for other things, I guess?
I think everything we've done here works for a solenoid.
Okay.
Now, whether it'll work for everything, I'm not so sure.
Okay.
But we got that. Well, so what?
What is the L in that formula? Not the big L, but the little L.
Oh, it's the length.
Length, okay.
It's the length of your solenoid. Thank you for asking. Okay, now we're going to move on here. I need a little room to operate. We've made a little progress there. We're talking about this stuff called inductance. And I'm going to draw you a picture of an inductor. There's one. Now, this happens to be on page 641. If you guys have a book, my book has it on page 641. Now, if you have an inductor and the current is increasing, let's say the current is going that way, and it's building, it's getting bigger and bigger and bigger. Well, Lenz's law says the induced magnetic field will create a voltage that will try to what's the word? Fight you on that. So what happens is, now there really isn't any battery here. There's no battery, but I'm just pretending so you'll understand. This thing, if that current is increasing, is going to act like a battery. You know, a battery wants to push the current this way. You know that a battery wants the current to go that way. And if you have a current that's increasing in your solenoid or any kind of inductor, it kind of acts like a battery. It has what they call an induced EMF, and it's going that way. Now let's look at a inductor where the current is decreasing. Here's this current. Now it's still going this way, but it's decreasing. See, what we just did was a current going this way, but it's increasing. And it kind of acts like a battery trying to shove the current the opposite way. Well, now if the current is decreasing, then what happens is there's an EMF that's like this. There really is no battery here, okay? It's just pretend, so you'll understand. But it's going to try to keep the current going that way. Inductors, the closest mechanical thing that explains conductors, I think, is the flywheel. See, a flywheel, you guys all know what a flywheel is. I have one in my garage. You know, it's a deal kind of like that. And it spins, and there it goes. I turn it on like that. I can take my screwdriver and I can stick it on there and sparks will fly all over the place. You know about flywheels, right? Well, it's really it's a grinder. I can sharpen a hoe or something on that grinder. But see, when you turn this thing on, it probably revs up to about 800 RPM. But it doesn't go to 800 RPM instantly. But when I turn the switch on my grinder, it'll start to turn. It'll go up to maybe 50 RPM, 60, 70, 80, 100, 200, 300, 400, 500, 600, 800 RPM. And that's where it stays there. Now, when I shut it off, it doesn't just stop instantly. It has to slow down. Inductors are the same way. They resist the change. You're trying to increase this current and it resists you. Here you're trying to decrease the current. With the grinder, when you turn it off, it doesn't go from 800 RPM to 0 RPM. It's going 800 RPM, okay? You turn the switch off, and then it'll slow down to 600, 500, 400, 300, 200, 150 RPM, and then it stops. It probably takes about 30 seconds for it to finally stop. I'll tell you how long it takes to crank up. I turn the switch and it goes. Now, how long did that take? 1001, 1002, 1003, 1004. It takes about 5 seconds for that thing to crank up. It doesn't go from 0 to 800 RPM instantly. And I'll tell you something about an inductor. The current in an inductor will not go from 0 to whatever, 10 amps, let's say, instantly. It will not do that. Now, you can do that with a resistor. If you have a resistor and there's no current, you can crank it on and get 10 amps immediately.
So does an inductor or does a solenoid kind of act as a shock absorber in a sense, or?
Yeah, it sort of smooths things out. Yeah, exactly. Now we're going to look at a circuit now with an inductor in it. And that circuit is found I might have to draw my own circuit. That's okay. We'll just draw one here. We're going to draw a circuit with an inductor in it. Okay, I need a little room, but now you understand about inductors. They're kind of like flywheels or grinders. And we understand about the units. You can express them as henries for sure. Yeah, they're in henries. Okay, here's our circuit. We're going to have a battery here. And we'll have a switch. We'll have a resistor. And an inductor. There we go. Oops. Here's your voltage or your EMF. There's your inductor. There's your resistor. There's a switch. Now we're going to throw that switch. Let's say there's no current. No current at all. It's kind of like that flywheel. It's sitting still in my garage. It's not spinning. And we're going to throw that switch. And when you first throw the switch, current wants to start going through the circuit because you've thrown the switch. But at that very instant that you throw the switch, there's no current at all. The current does this. It starts off at 0 and rapidly increases until it reaches, here, let's give some numbers. Suppose this was 6 volts, 6-volt battery, and this was a 2-ohm resistor. And let's have this be a 8 Henry coil. 8 Henry inductor, there we go. Now, after a while, when the current smooths out, there's no more voltage on the inductor at all. See here, let's draw the voltage on the inductor to start with. This is the voltage on the inductor. When you first throw that switch, you're going to have 6 volts on that inductor. And they're going to be plus minus like that. And 0 volts, you're going to have 0 volts on the resistor. How come when you first throw the switch, there won't be any volts on the resistor? How come?
Because there's no current.
Because there's no current. If there's no current in a resistor, there's no volts on that resistor. Good going. But what happens is, go ahead.
What is that underneath on the graph that you have on the bottom where we're looking for the voltage of the inductor? What is under that?
This is the voltage on the inductor. And
but what's under that? Does that say CV?
It says 6 volts.
Oh, okay. Thank you.
Anytime. See, you'll have 6 volts. And then what happens is, as it smooths out, and it'll reach a current of 3 amps. And it'll reach this asymptote. It'll reach a 3 amp asymptote. But the voltage on the inductor will do this. It decreases exponentially like so. And
Could you re-explain what the y-axis is on the second graph?
yeah, that's the voltage on the inductor. That's V little l.
Voltage on the inductor. Okay.
Voltage on the inductor, yeah. It starts off when you first throw that switch. When you first throw that switch there, you'll have 6 volts on the inductor, 0 volts on the resistor.
What is the CV then?
The CV.
6 volts.
Yeah, it's 6.
Oh, 6 volts. Oh, okay, got it. Okay.
Good going. Now we could also draw a graph of the voltage on the resistor. See, it starts off as 0, doesn't it? Because there's no current when you first throw the switch. And then it does this, and it will reach a maximum value of 6 volts. Because you'll get 3 amps in a 2 ohm resistor that gives you 6 volts. It makes sense. The voltage on the resistor will just copy the current. And now let's look at the voltage on the inductor. We need a little room here someplace. How about right here?
Did that.
We're going to do the voltage. Oh, I already did that. Never mind. I already did that. The current on the inductor is the same as the current anywhere. It's a series circuit. So I think we got everything. We got everything. Now the equations for this stuff go like this. The current is equal to your 6 volts divided by your resistance. And this is your time constant. And the time constant is L over R for these are called RL circuits. That's what we're studying right now. We are studying RL circuits. And that's the equation for the current. Now, if you want the voltage on the resistor, here's the equation for that. It's going to be, in this case, just like that. Now let's look at this time constant for just a minute. The units on L we decided are ohm seconds. And the units on resistors are ohm. So guess what? You get seconds, don't you? Well, that's what time constants give you. Time constants give you seconds. Hey, we got a whole lot more wonderful students that have tuned in now. Hello, everybody. We've got Melissa, Mohammed, Mark, Levi, Jeff, Brendan, Ben, Logan, Chris, great group. So that's what we're studying now. We're studying these RL circuits. And those are the equations. Now, if you want the equation for the voltage on the inductor, let me write that for you. The voltage on the inductor is going to be, in this case, where this tau is our time constant. Now, here's how I remember this. You might wonder, well, is it R over L or is it L over R? Well, the way I remember it Well, one way is by looking at the units. See, the units will tell you it's got to be L over R. But the way I remember it is in the alphabet, L comes before R. A, B, C, D, F, G, H, I, J, K, L, L, M, N, O, P, Q, R. Hey, you know what? L comes before R, doesn't it? That's how I remember it. Or you can use this ohm seconds over ohms, give you seconds. This is an exponential decay. The voltage on the inductor starts off at 6 and it drops down to 0. So there's your LR circuit. We probably should practice that with some, let's practice that. That's what we'll do. But I want to show you one thing before we practice that. I think I was telling you guys about the energy stored in inductors. The whole purpose of an inductor is to store energy. Is that how you spell purpose?
Yeah.
I think so, yeah. The whole purpose of an inductor is to store energy. You know what? That's the purpose of capacitors too. Capacitors store energy in electric fields. Inductors store energy in magnetic fields. Now I'm going to show you the equation. Here we go. We're going to do a KVL. You all know what that means, KVL. Goodness knows we've done many of those. Kirchhoff's voltage law, we're going to go around this circuit and you'll have a plus EMF minus IR, V equals IR, that gives you the voltage, minus L di dt back to 0. Remember the voltage on an inductor is equal to minus L di. It's just another form of Faraday's law. We had that, I think I wrote it as a voltage like that, the induced EMF on the inductor. Okay, now follow me. We're going to do some algebra here. Got 2 steps and we'll have the energy stored in your inductor. Multiply everything through by I. That's legal. That's a minus sign. No, yeah. I multiplied by I and then multiplied by I. I'm using capital letters. I'm mixing my letters here. I guess I need to be consistent. Let me use little letters here. We'll try to be consistent. Now, can y'all, little Southern talk, y'all get from here to here? All I did was multiply by that little I, and that's certainly legal in any equation. Now, this is volts times amps. You know what that is? That's power, isn't it? Remember, power is volts times P equals IV, I think is the way we wrote it. P equals IV.
Yeah.
Yeah, because see, volts is joules per coulomb. Wait a minute. Yeah. We've had that equation many times. Here, let me write it out for you. That's coulombs per second. And that's joules per coulomb. This is the sort of thing we did on our dimensional analysis. And so you wind up with joules per second, which we all know is a watt. So this is power. That's the power the battery's providing. Well, this I squared R, hey, we've seen that before too. We have seen P equals keep mixing my big I's and my little I's, but that doesn't matter. P equals I squared R. That we know and love that equation. That's the power that a resistor is using. So guess what this has to be?
0.
Well, this isn't going to be 0. It's going to be the power. That's power, that's power, that's power. We're talking power that the inductor is storing. It's the power in an inductor. So let me write that someplace up here. This is the power. Now, one way of writing power is the rate of your energy. This book uses U for energy, I believe. Power is the derivative with respect to time of your energy. And it's equal to, now I know there's a minus sign there. You can put an absolute value if it'll make anybody more comfortable. Whoops, I forgot my I there. I'm just interested in the magnitude of this power. You're either storing the power or you're releasing the power. You're storing the power if the current is increasing, and you're releasing the power if the current is decreasing. But let's don't worry about plus or minus here. And what we're going to do is we're going to do some algebra with that. Never mind this P. We all know that we're dealing with power here. Can you get to here with me? All I did was get rid of those DTs there. I lopped them off, and I have the differential of your energy is equal to IL times the differential of your current. If you can get to here, we're almost done. We're going to take and we're going to integrate here. And what you'll get when you integrate that is you'll get your energy stored from start to finish in your magnetic field. And you guys know that this is going to be I squared over 2 times L. You have to plug it in from 0 to some final value. And what you wind up with is 1/2 IL squared. The energy stored.
Wait, you mean I squared L, right?
Yes, I was wrong, and you're absolutely right. It's 1/2. Here, let me write it this way: 1/2 LI squared. And there's a thank you point. Appreciate your help. Now you're going to see that equation. Let me show it to you in your book. Dig around here someplace, see if I can find it. I don't see it there. Keep looking here. There it is. I happen to see that equation on page 649. Well, I think we should do some examples of these things. Let's suppose you had that same circuit that I had here, 6 volts, 2 ohms, let's get rid of that 0 volt thing there, 8 henries. That's our circuit. And what we're going to do is we're going to find the energy after your switch is thrown, after say maybe 2 seconds. Find the energy 2 seconds after you close the switch. That'd be fun for us to do. Here's our circuit. We have our equation over here someplace. There it is. We have numerous equations here. Let me write them for you, and then we'll calculate some stuff. Find the energy after 2 seconds stored in the inductor. Find the current. That would be fun. After 2 seconds after you throw the switch. Okay. Maybe find the voltage on the resistor. All kinds of questions I could ask you. Well, that's enough. We'll find those. Okay. Well, we need the equation for the current. Now the current goes like this. In this case here, it would be 6 divided by 2, it'd be 3 amps. And the tau would be 8 over 2, which is 4. There's your current.
Is the current uniform across the circuit, or is it different at different locations?
Well, it's a series circuit, so all the components have the same current.
Okay.
Now, I want you to plug in 2 seconds for time and get me the current. I'll wait. I'm going to do it too if I can find my calculator. Here it is. I think that you guys have a homework thing that's due tonight. You've probably already done it already. I might give you some more homework that's not to turn in, but there's one to turn in. I know that. See, I've learned how to grade your homework. I'm coming along here.
Mr. G, what is that underneath the negative time?
It's a 4.
Okay. And where did you get that?
Remember, the time constant is L over R. In this case, it's 8 henries over 2 ohms. That gives you 4 seconds.
That's what I thought. I just wasn't sure. Thank you.
Thank you for asking. Was that Melissa?
Yes, sir.
Yay, I'm learning your voice, Melissa. I got an answer. Did anybody get 1.18 amps?
Yeah.
Yay, I heard a yeah. Well, great. Now look here, we just found the current. Check, we just did that. Now, if that's the current, what's the volts on the resistor? Volts on the resistor will be V equals IR.
Would R just be 2 ohms in this case?
Yeah.
Okay.
V equals IR. I'm getting the volts on the resistor is
2.36.
2.36 volts. Yay. Check. We just did that. Excellent. What about the energy? energy stored in the inductor? Let's do that. Well, we have an equation. It's 1/2 Li squared. So square the I times the L times 1/2. I got an answer, but you better double check me. You know me, I'm capable of pushing the wrong buttons. Did you get 0.1794 joules? And I'll wait because I want to.
Oh wait, let me divide by 2. I got 5.56.
I could be
Yeah,
wrong.
me too.
Let me
I
do.
also got 5.57.
I'm doing mine over.
Yeah, 5.7.
Yeah.
This is wrong. See, I do this on purpose to try to boost you guys' confidence. Don't you feel better now? How about that? 5.569. Yay, we got it. That energy is at that instant now is being stored in that magnetic field. Okay, well, that was fun. What about, I didn't ask you for the voltage on the inductor. I want you to go ahead. I'll shut up. I want you to find the voltage on the inductor after 2 seconds after you throw the switch. I'll be quiet, and let's see if you can find the voltage on the inductor. Well, I got an answer. Did you get the voltage on the inductor is 3.64 volts?
Yes.
Oh.
Yay! Good going. Does anybody need help with that? You're okay.
Yeah.
All right, good. Notice the voltage here is plus minus. The resistance or the voltage is plus minus. The voltage is plus minus, and they should add up to 6. Does 2.36 and 3.64 add up to 6? Yeah.
Yep.
It works. Okay, great. Well, let's do another one. I'll give you another problem. Here we go. And here, let me write down the homework here. Now, this is not to turn in, because you have one to turn in that's due tonight. The beauty of these things that are not to turn in is I can help you with it next session and show you how to do it. But the stuff to turn in, I can't give you the solution until I grade your paper, right?
Mm-hmm.
Theoretically. Okay, now this is don't turn this stuff in, but do it. And we'll do some more problems here in a minute. Do these two for me. Man, that was a weird sound.
Sorry, that was my chair.
There's some homework.
Needs oil.
Yeah. I thought it was a Shamu, the whale, making a sound there is what I thought it was. Okay, well, Do that for homework. That'd be good for you. All right, well, we're going to do another example. Unless you had a comment or question. And you know what? There's only this week and next week. I think it'll be over. Don't you think?
Really? This week and next week, and then it's done?
Well,
Yeah, that's it. This week, next
Wow.
week, and then we have finals.
Jeez.
let me look at the, this is the Monday. This is
20th.
the 20th.
Yep.
Wednesday is the 22nd. And then the
Wow.
next Monday is the 27th, right?
Yep.
And then that Wednesday. And of course, you're going to get wonderful lectures on all those days. And I'll record them so that you can pull them up if you can figure out how to do that. Now this is April. 30 days hath September, April, June. There's 30 days in April, isn't there?
Yes.
Yes.
So Monday,
The Monday after that will be the 4th.
not that I don't trust you guys. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, 29, 30, 1st, 2nd. It'll be the 4th, won't it?
Mhm.
Yeah. Well, here's what I plan on doing is giving you your take-home final, and it would be due. It would be due the 6th. I could give it to you that Sunday night, maybe. Your final, take-home final. What do you think of that idea?
Sounds good.
Take-home.
That
final?
works. That works well because my calculus class is giving me a 3-hour final, so I just have to. She's giving a very narrow window, and it cuts into this class that's going to work out very nicely for me.
Good. Well, you'll have time to work on it and do a good job for me. And then,
Will all
Professor
4 of
Griffin, are you
them?
going to do that for all 4 of your classes?
I'm thinking of it. Yeah.
So you'll just give us all of our finals on Sunday, and then they'll all be due on the 6th?
Can you handle that?
Yeah, that's perfectly fine. I was
Yes,
just
sir. That's
clarifying.
fine.
Well, let's do it that way. That sounds good to me. And that way I'll have time to, that weekend, get them all graded and entered into your books and figure out your grades.
Professor.
Yes.
So are you planning on doing all 4 Sunday to Wednesday, or are you going to do 2 Sunday to Wednesday and then 2 Monday through Thursday?
I might change my mind and do, like you said, a Tuesday through Thursday. It's quite possible.
Okay. But we will have 48 hours at minimum.
How many hours is that? If I gave it to you late Sunday and it was due Wednesday, how many hours is that? Sunday, Monday?
72 hours if it's late Sunday.
Yeah. That's more than 48 hours, isn't it?
Well, I'm saying at a minimum, it'll be 48 hours.
Yeah.
Yes.
Okay.
Absolutely.
Awesome.
Yeah.
Thank you, sir.
I think it'll work. Okay.
That's better. That's better than my hour-and-a-half window that I had for my DiffEQ final.
Yep.
Oh, I pity you.
Yep.
I pity you. Well, this is all new to me. I still don't know how my daughter figured out how to record these and put them on YouTube. Have any of you looked at the YouTube stuff?
Mm-hmm.
It works.
Yes, sir.
Yeah, it worked just fine.
Yes, sir. It does work.
Good. Excellent. Well, she's going to record this when we get through. Okay, let's do another one. Now, let's suppose we'll do this a little different. Suppose you have a battery and our friendly switch here, and a resistor, inductor. Okay, we'll make up some stuff. 12-volt battery. 3 ohm resistor, and 9 Henry inductor. And what we're going to do is we're going to throw that switch And the inductor, acting like a flywheel, starts off with 0 current, and it builds to a maximum of 4 volts, right? Not 4 volts, 4 amps.
Yes.
3 into 12 gives you, yeah, it'll build up to 4 amps. Here, I'll draw you a graph of it. The current in this circuit starts off at 0 and builds up to a steady 4 amps. Now, once that current is steady, there's no more voltage on the inductor, because remember, the voltage on an inductor, according to Faraday's law, we'll use this version of it. If the current is constant of 4 amps, what's the derivative of a constant?
0.
0. So after a while, after a long time, this is time here, there is no current or no voltage on the inductor at all. 0 volts.
Mhm.
And then what we're going to do is, see, that's when you pop this switch. You close that switch, and that's the situation. We've got 4 amps in the circuit. And now what we're going to do is we're going to have another switch here. And simultaneously, we're going to pop this switch open, bam, and close this switch here, bam. So here's the situation. We've cut the battery out. And we're going to start over on our stopwatch. Battery's no longer in the circuit, but we have that 4 amps. But remember the flywheel? It's going to die out. It's like you shut the flywheel off and it starts slowing down till it stops. So at time 0, we have, it's a little different story now. We're going to start our stopwatch. When we throw those switches, the battery is no longer part of the game. And this is all we got here. And we have 4 amps. And you know what'll happen. You'll have a circuit like that. And here's how it works. The current will be 4 amps e to the minus t over tau. Now what I'm going to ask you is, let's say 3 seconds after you pop those switches, 3 seconds after you pop those switches, we know what's happening right here at time 0. We have 4 amps. 3 seconds later is over here someplace. 3 seconds later is over here someplace. I need to know the current, the voltage on the resistor, the voltage on the inductor, and the energy stored in the inductor. Ooh, that would be a good little problem to do, wouldn't it? I'll show. Go ahead.
The second voltage is VL.
Yeah, this is the voltage on the inductor.
Okay.
Why don't we start with that? I'll shut up for a minute and see if you can. You got the formula here. See if you can get the current 3 seconds after this circuit has started. The current is decreasing. Go for it.
I'm looking at the last problem. And my formula is slightly different.
Yeah, the
I
formula
have a
is
1
different.
minus. Okay, it is different. Okay.
It's totally different.
Okay.
Because there's no battery in this one.
Okay.
The current is not increasing, it's decreasing.
So we're finding the current and the voltage on the resistor. And what's the third thing again?
Kind of hard to read there, but it's, did it come off of the,
Yeah.
there, that's better.
That'll be fine. Yeah, that's better. Yeah, I got it.
It's the total energy storage.
Okay.
But thank you for asking.
You're welcome.
Well, I got the current. I wonder if I did it right. I'm getting 1.47.
Yep.
Yep,
Yes.
I heard a yep.
Same.
Up to 2 amperes. Does anybody need help with that? We got some wonderful students here. I see Nathan there and Melissa. Jeff is helping us today. I mean, Adam is helping Jeff today, which is great. Well, I don't guess you need any help. I guess you're able to get that okay. Now let's get the voltage on the resistor. Well, that would be did you get 4.415 volts on the resistor?
Yes.
And remember now the current's going this way. It's decreasing though.
Mm-hmm.
So this thing's going to act like a battery. Remember, there really is no battery, but if there was, you would have a negative and a positive like that. It would try to force the current through there. And so this end is plus minus. And of course the current is going clockwise, so this end is plus minus, but that's minus plus. And I'm getting 4.415 volts plus minus on the resistor, 4.415 volts minus plus on the inductor. So that you get the same amount, 4.415. Now, I don't know how you could write that. I guess you could put a minus in. If that makes you happy, put a minus there. But see, I know what it's doing. It's doing this.
Because they need to equalize, right?
Yeah, it has to add up to 0.
Okay.
Another way,
equal but opposite.
equal but opposite. Another way of looking at it is they are really in parallel. It looks like series, doesn't it? But if you consider this point here and this point here, see, here's your 3 ohms, and here's your 9 henries, and they meet up. Call this point A and this point B. Here's where students get confused. They look at this and they say, well, that's a series circuit. But look, if you look at it this way, the ends are connected. That's parallel, isn't it?
Mm-hmm.
Parallel. And what do you know about parallel? You know the voltages are the same.
Yep.
The minus plus and the minus plus are the same because they're in parallel. Okay, now we did good. Now let's get the final or the total energy stored. I need some room. We'll write it up here. That's 1/2 Li squared. Okay, I'm going to do that now. Here goes. 1/2 L is 9 henries. Current is 1.472 squared. Well, I got an answer. I'm getting 9.75 watts. And I'll wait for an
Yeah.
Yeah, I heard a yell. Good going.
Yes, sir.
Yay, good going. Proud of you. Okay, well, what did we do today?
It was 9 point what?
9.75.
And
Yep.
yeah, 9.75 watts. 9.75 watts. Well,
So,
let's
Mr.
see.
Griffin,
Yes.
can you explain me one more time why we get the voltage of inductor as a negative of 4.415?
Yeah. The current is decreasing. You see this current here? It's decreasing. It's getting smaller. And so the inductor, kind of like our flywheel, it's got inertia. It sort of fights that. It doesn't go to zero immediately. And so what it tries to do is it tries to keep going. See, the flywheel tries to keep going for a while. It takes maybe count to 20 before it finally stops. It tries to keep going because of inertia. So
It has stored energy, kind of like a capacitor.
yeah, it's got energy.
Okay.
It's got and it tries to push through the current. It acts sort of like you had a battery there. See, if you had a battery there, that would try to keep the current going, wouldn't it?
Yeah.
Does that help?
Yeah.
Yep, that's it.
Your watt should be joules, correct?
I am wrong, and you are absolutely right. It's joules. Thank you so very much. The energy stored at that moment is in joules, not watts. Very excellent. It's easy teaching this class. Anybody else comments or questions?
Would they have different not charges, different currents? If we're thinking of it as a parallel circuit, then would there be different currents?
Yeah, oh, that's an intelligent question, because in parallel circuits, the voltages are the same. We understand that. Voltages are the same, but the currents could be different, couldn't they? But not in this one. In this
Okay.
in this one here, whatever that current is, where is it? There it is, 1.72. It's going this way, around here, and it has the same current. Yeah.
You could also see it as the inductor as being a battery, and the resistor is going to have the same voltage as the battery because it's in series with the battery.
Yep.
You don't want to look at it as parallel.
You could. Yeah, you could. That was good. If you like that better, I'm happy with it. Anybody else? That was an intelligent question. Well, okay, I think that's about it for today. This will be on YouTube when my daughter gets home from work and figures out how to put it on YouTube. She's good with this stuff. And I gave you some not to turn in, and there is one for points that it's on Blackboard. Do that, and I'll grade it and post it hopefully tomorrow. Well, I've had a good time, and Unless there's anything else, I'm gonna end the meeting.
Alrighty.
Okay,
you,
guys.
Sounds good
Professor.
to me.
I'll see you. I'll see you. Some of you soon, I hope. End meeting.
See you
Goodbye
on
now.
Wednesday.
See
See
you.
Alright,
Yeah.
bye-bye.
See you tomorrow.
See
Bye.
you tomorrow.